Lock Manager ensures of correct running of the locking protocol by keeping track of locks issued to each transaction. As we briefly discussed, this is performed using a lock table, which is a hash table with the data object identifier as the key. The object can be a file, page, or a record, based on the decided granularity level for the object. The entry for the object includes transactions that have a lock on the object, whether the lock is shared or exclusive, and the pointer to the queue of locks requested on the object. The database management system also handles a transaction table that contains the list of locks that each transaction holds. When a transaction needs a lock, it should request that lock. It submits the request to the lock manager. If the request is for a shared lock, and currently there is no exclusive lock on the object that prevents it from being granted to a shared lock, the lock manager grants the lock and updates the lock table entry for that object. If the request is for an exclusive lock, the lock manager ensures no locks are granted or requested in the queue for this object and grants the lock. Otherwise, in all of the other cases, the lock cannot be granted and the request should be queued. One case that we should be careful is the case of shared lock request arriving after an exclusive request when an object already has a shared lock. For example, say transaction 1, T1, has a shared lock on object A. Then T2 arrives and asks for an exclusive lock on A, and therefore the request is queued because we cannot grant exclusive locks on objects that already have a shared lock. Then T3 arrives and asks for another shared lock on object A. Even though T3 needs a shared lock and it can have access to the lock while it currently has a shared lock, we have to ensure it is queued after T2's request for exclusive lock. Otherwise, we might starve T2. Starvation is a situation that a transaction waits indefinitely while a stream of other transactions acquire locks. If we keep granting shared locks, ignoring the exclusive lock requests in the queue, starvation can happen. With requesting and granting the locks and awaiting the queue for lock releases, there might be, in a few occasional cases, a deadlock situation. First, let's see why deadlocks happen. Assume two transactions, T1 and T2. Say T1 needs an object A and puts an exclusive lock on it. Then T2 needs another object, B, and there is no conflict, so B puts the lock on it. Then T1 needs B that T2 just put a lock on, so it has to wait in the queue till T2 releases the lock on B to acquire it. Then T2 enters the part where it needs A, and it also puts a request for a lock on it that needs to wait on the queue. So now T1 is waiting for T2 to release the lock on B, and T2 is waiting for T1 to release the lock on A. And both of them need the locks before they can release the locks they have. This situation is called a deadlock. Deadlocks are typically very infrequent and involve very few transactions. However, if we do not deal with deadlocks, they might affect the performance of our database management system. In order to deal with deadlocks, we need to be able to either prevent them or identify and resolve them when they happen. Let's start from detecting and resolving, and then we will see how we can prevent deadlocks.